Let us understand how we develop a distribution for a random variable with a very simple example of coin tosses and study the nature of this to build our understanding of the random variable and probability distribution. We'll start with a simple example and then we'll keep on building with more complexities going forward. So let us say we are tossing one coin and our random variable is number of heads that we get on tossing a coin. So now we'll start with the first coin toss where there are two possibilities, head and tail. Now I'm going to templatize in such a fashion that I can copy the formula for the more complex scenarios going forward. So let us see, we want to calculate the number of heads in a single coin toss. So count if range, let's say up to 3 coins, comma, if it is head we count it, otherwise we say we don't count it. So there are two possibilities, 1 and 0. So let us say we want to count this random variable with 1 and 0 head. Let us count the frequency of head, which is 1 and in one coin toss, and the frequency of tail, which is also 1, which is equal to 0 head. So we will use the formula is equal to count if this range, comma, the number of head, 1, and I can copy it underneath. So we have 0 head, that is which occurs with the frequency of 1, 1 head with the frequency of 1. So now we have the frequency. We can now compute the relative frequency, which is your probability of occurrence, is equal to whatever that frequency divided by sum of the all occurrences, which is 2 in this case. So the relative frequency is 0.5. We copy this formula underneath. So probability of 1 head is 0.5, probability of 0 head is 0.5. We know the formula for xpx and for expected value of x. So we can use the formula is equal to sum product, which will take the array x comma px, right? So the expected value when you toss a single coin is 0.5. Half a head is the expected value in this experiment. Now we can compute x minus e of x is equal to x minus e of x, which is 0.5, and we copy it underneath, which is minus 0.5. We know the formula for variance of x, which is x minus e of x whole square times p of x. So we'll use the formula sum product x minus x comma x minus e of x comma p of x. So I'm including this x minus x twice so that it is squared, and then add these products to get the variance. which is 0.25. We can do this using the binomial distribution formula also, which allows us to do this, is equal to binom dist number of success, that is the number of heads, comma number of trials. In this case we are going to do one trial, comma what is the probability of success is 0.5, comma whether we want the cumulative or the non-cumulative, we'll go with the non-cumulative, and close the bracket. So what we calculated using the relative frequency formula can be calculated using the binomial distribution. Because it's a single coin toss, it was very easy for us to calculate these, but when we have the large number of coin tosses, it becomes a little difficult. So now this is the case of single coin toss. Now we can represent this in the graphical format also. X, P of X, that will give us the graphical representation of the probability distribution. Insert. Okay, so let me fix this. The blue bar is 1 and 0.5 and the orange one is 0.5. This is P of X and this is also P of X. Okay, so it has done it this way, but we need to have the labels to be here, and let's remove the series, and series name is this, and the series values are 0.5, 0.5 each. It should be 0 and 1 and 0. Alright, so now when I click OK, the chart is representing what we want it to represent. So I can just make it a little simple so that we see what we need to see. Alright, so we have got, let's change the scale to 0.5 so that the bars are sufficiently tall. Okay, so we see the discrete distribution, the binomial distribution for a single coin toss is a equally heighted 0.5, 0.5. Let's extend this experiment to 2 coin tosses. In 2 coin tosses, there are 4 probabilities: head, 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 tail, tail, head, tail, tail. Now I can use the formula which I used here because it is copyable, and we directly get the frequencies of the occurrence of head in each of these possibilities. So now when we have 2 heads 2, 1 head 1, and 0 head is double T. So we can use the formula the way we used here, is equal to count if, select these values, comma 2. So we can copy this down. So we have 1, 2 and 1. The relative frequency, that is our probability, is equal to frequency divided by sum of all occurrences. I can copy it down. What is the expected value? Is equal to xpx, some product x comma px. And once we know the e of x, we can calculate x minus px is equal to x minus e of x. All right, and now we can compute the variance of it, sum product x minus e of x, x minus e of x, x minus x square times px. All right, variance is 0.5 and the expected value is 1. We can compute it using the binomial distribution also. All that I need to do is copy it here and just change this 1 coin to 2 coins. Let's see what else I need to fix. B10, number of success, trials 2. Okay, probability of a single success is 0.5. So how do I fix it? We can call that probability of single success as bias term because we can modify it. So let's, instead of E10, let's point it to the 0.5. And then when we compute it, we get the number. So we can do it here as well so that we are not relying on the value where the bias term or the probability of success of a single outcome and the probability of success in a multi-throw outcome is same. Now we can, let's copy this chart and see if we can gain some advantage. So let's change the data range. Instead of this, we want it to follow this. So we have got the probability distribution of 2, 1 and 0 head, which is different from this equal probability to double chances of getting 1 head and half chance for 2 heads and 0 heads. We can now extend this experiment to the 3 coin tosses. So there are these possibilities which I can just copy paste here, copy paste it again, and here we will keep H and T. So there are 8 possible outcomes and we can use the formula from here and paste it here to count the number of heads in all possible outcomes. So 3 heads, 2 heads, 1 head and 0 head. Now we can use the formula for frequency here is equal to count if comma 3. So we got this 1331. So the probability of X is total frequency divided by the sum of all occurrences. So I can copy and paste it here. The binomial formula should also work, just that I need to change it from 2 to 3. Right? So we're using binomial distribution also, we can get the same values. What is E minus E of X? Oh, we need to calculate the E of X first, is equal to xpx, which is same as sum product, x times px, which is 1.5. We can calculate the x minus e of x is equal to x minus e of x, and I can copy this formula underneath here. And now v of x is sum product of x minus e of x comma minus e of x comma p of x. So the v of x is 0.75. Let's copy this chart one more time. And let's change these values to refer to the new case. All right, so 3, 2, 1, 0. So we have these two bars of same height, and these are 1/3 of the heights of these two bars. We can also see that all the time we have the sum total of these binomial distributions is 1. We can directly calculate the expected value of x for a binomial distribution, which is given by np is equal to n, which is 3 here, multiplied by p, probability of success, which is 0.5, and v of x is npq is equal to n, which is 3 times p times 1 minus p, which is your q. So we can determine it using the direct formula also, using the binomial distribution. Let's conduct this experiment for a 4-coin toss and see how the distribution of each of these cases differ. So I can copy this, Control C. Okay, we need more space, that's okay. And I need H at these places, and I need T at these places. Now I can do the count is equal to count if range comma if the number of H. Let H be capital. And I can copy this formula underneath, double click, and all the values are copied here. Now we have case of 4, 3, 2, 1 and 0. We can calculate the frequency, count if if 4, and double click this. So okay, I don't need this, delete it. P of x is the relative frequency divided by the sum of all occurrences. Alright, I must increase the level of resolution so that it is 0.0625. E of x is equal to xpx, which is same as sum product, x times px. And similarly we can calculate the v of x, which is sum product. Okay, we need to calculate the x minus e of x first, is equal to x minus e of x so expected value is xpx. Oh, we already have that. The variance is sum product of x minus ex comma x minus ex comma e of x. We can use the binomial distribution formula also to do the same computation. Binom dist, number of success 4, number of trials which is 4, comma probability of success is our bias term, comma we don't want the cumulative one. And we can see that the values are exactly same. We can use the formula NPQ and NP. We will need to change the values. Okay, let's directly take 4 times 0.5 is equal to 4 times 0.5 multiplied by 1 minus 0.5. So we can calculate it using the binomial distribution properties, or we can calculate it using the first principles. Let's copy and paste this chart one more time. Control C, Control V. Okay. V. And change the referencing. Alright, so here is the distribution. We can see that the distribution nature changes as the number of tosses increase. Now that we have understood how we do a probability distribution of 1 coin, 2 coin, 3 coin, 4 coin, now we can do the distribution for, let's say, 100 coins. So this we can now directly do using the binomial distribution formula. So let's do it for the 100 coin tosses. So x with 100 coin tosses. So we need a sequence rows. We need 101 rows, no columns, starting at 0 in steps of 1. So we will go from 0 to 100. Those are the number of heads possible. We can have p of x, which can be computed using binomial distribution. In fact, we can, binomial dist, number of success is here, number of trials. Let's kind of keep it aside, or maybe I can just put 100 here. 100. Probability of success is 0.5, comma, I don't want this to be cumulative, enter. Now this is the probability of 0 head in a 100 coin toss, and now I can get the probability distribution of 100 coin tosses. And then now I can copy this one more time, put it here, and change the referencing. So I can drag it here, drag this thing, okay, looks like it's maintaining the referential integrity. Okay, I can just go and change from here, select data, edit, axis labels are here, okay, p of x, edit, this value goes up to 101. Yeah, 102, from 2 to 102. Okay. Okay. Let's verify. Yep, we have done it correctly. Now we can enlarge the size of this chart to see the probability distribution. Now the highest probability is here, which is about 0.0. So let's make the scale 0.07. Okay, 0.08. Alright, so here is the binomial distribution of 100 coin tosses. So we are able to generalize this distribution to a large number of cases. Now we can play around where if the probability of success is not 0.5, we can generate the all kinds of distribution. So let's say instead of 0.5, it is 0.1. The distribution shifts here. Of course, I've truncated it, so it will become larger up there. If it is 0.75, the distribution shifts here. So we have got a family of binomial distribution for different success probabilities of each trial. So this is how we can develop the distribution.